Hello, this is a Bayesian approach to media mix modeling using PyMC3. My name is Mike Johns. I'm a data scientist at HelloFresh in the US. The work I'm going to present today has been done in collaboration with my colleague, Zhenyu Wang, who's a senior business intelligence analyst at our offices in Berlin. We'll start off with a brief overview of marketing at HelloFresh, explain what a media mix model is, talk about the structure and function of the model we built in PyMC3, touch on our Bayesian model building workflow, and then wrap up with a discussion of model applications and business use cases. For those of you who aren't familiar with us, HelloFresh is a meal kit delivery service. When a customer signs up, they select the number of meals they want and the specific recipes, and then 5 to 7 days later, they get a box of ingredients and recipe cards that allow them to make a fresh, hot meal. We currently operate in 14 countries. We started in Germany in 2011. Our US operations launched in 2013. And this year, we added our newest country to the mix, which was Denmark. For the last 7 to 9 years, our major focus has been growth. And so marketing has played a critical role in that business goal. Our yearly budget is about $300 million. And our marketing is varied and it involves a complex mix of channels in both offline and online segments. So that's anything from Facebook and Instagram to television and billboards. We use marketing throughout what we refer to as the marketing funnel. So in the upper funnel, you have channels that tend to be offline, things that build awareness of the brand. In the mid funnel, you have a mixture of more online and offline channels that are designed to build on that awareness. And then at the bottom of the funnel, you have what are mostly referred to as direct response channels, things that allow people to translate their interest into a conversion. So these are sites like Groupon, app stores, and most familiar to most of us probably is search engine marketing. So measuring and optimizing our marketing effectiveness is a key data science task that we engage in as we try to grow the brand and achieve profitability. So how do we measure the effectiveness and efficiency of our marketing? The primary way we do this is by looking at the cost to acquire a customer. And that is simply the amount of money we spend in a particular marketing channel divided by the total number of customers we acquire through that channel. And the primary means we use to understand what channels are driving customer acquisitions is through voucher redemption. So typically when you see an ad, it will be accompanied by an offer and a promotion code. And so you as the prospective customer are encouraged to go to our site, sign up, and redeem that code. And in doing so, that gives us information about the marketing channel that was the primary driver of your becoming a customer. Now, there's a number of limitations and challenges that arise when we try to measure marketing this way. So in a digital space, voucher attribution works fairly well because there's little friction between seeing an ad in your Facebook feed, clicking through it, and signing up using that code. However, when it comes to offline channels, the voucher redemption approach can be a little tricky. So you might imagine seeing an ad on the bus or on the subway, thinking this is an interesting product, I want to look into this, but it's sometime later before you actually have the chance to go online. And at that point, you've probably forgotten the code. So we might not be able to get a clean read on the fact that it was really that advertising in public transportation that brought you to our site. So there are methods for measuring offline marketing, such as lift tests or non-experimental approaches like geo-experiments, but those can be done only every once in a while. So for an ongoing measurement solution where you can track the effectiveness of your marketing on a weekly or monthly basis, voucher redemption has some serious limitations. So this is where media mix modeling comes into play. A media mix model actually offers a really elegant solution to these challenges of trying to get a comprehensive view of marketing effectiveness from both online and offline channels simultaneously. So the media mix model is a fairly old concept, and it's simply a multivariate regression model that is built to estimate the impact of your marketing activity, in our case, the amount we spend in a channel, on some key performance indicator. So for us, that is the number of new customers we acquire. So this basic idea was put forth in the 60s by Neil Borden. And traditionally, these models have been built using frequentist ordinary least squares methods. They're quite popular across a number of different industries, though they fell out of favor somewhat 10 to 20 years ago when digital advertising and digital measurement became the real hot topic in marketing. But there's been renewed interest as people have begun to realize that digital measurement has a number of limitations, those of which I discussed earlier, which is difficult to measure online channels simultaneously. So media mix model has a basic linear regression structure because it is essentially a linear model. So in our model, we have an outcome, which is the number of customers we acquire each week. And then we have a set of focal predictors, which in this case are variables representing the amount of marketing spend in each marketing channel. Now, typically what's done is these channels are transformed using two types of functions. First is a nonlinear function that allows us to account for the diminishing returns on advertising. And the second is what's called an Adstock transformation. And this allows us to capture and model lagged effects that advertising can have over time. So for example, it's typically assumed that marketing through television has an Adstock effect, meaning that the effect of that advertising is going to stretch out over some period of time, decaying at some rate. And then finally, we include control variables to capture seasonality, changes in some of our discounting tactics that we use. We can also include secular trends that capture market dynamics like interest in meal kit services in general. So just to touch on these transformation functions briefly, as I mentioned, the first function gives us a way to model diminishing returns. And we use a nonlinear function, logistic-like function with a single parameter mu. And mu controls basically how quickly the curve will saturate. So when mu is low, say around 1, you get a fairly linear effect. But as it increases and say at a mu of 7, you get a very saturated curve that rises quickly and plateaus quickly. Adstock, like I said, is a function to measure how advertising effects carry over and decay over time. So we typically use what's referred to as a geometric decay function. And the primary parameter there is alpha. And this is basically the decay rate. So as alpha increases, the rate of decay slows over time. So here you can see that with an alpha of 1, you get a very short decay, basically about a 1 week, 1.5 week time frame. But as you move up in alpha and get to around 0.8, the decay rate slows. And so the impact of that marketing is carried out over a longer period of time. So this is just a plot to illustrate what those functions do in practice when you apply them to some raw data, which is represented here by the black line. So the blue dotted line is that same raw data transformed with our reach function and a mu of 2. And so you can see it puts an upper limit on how high that value can go, which is a way of representing a saturating effect. The red dotted line is the same spend variable that's been transformed with an Adstock and a decay rate of 0.7. And so you can see here that that Adstock essentially smooths out the pattern and sort of eliminates these peaks and valleys, which is caused by the effect of the marketing dollars being stretched out over time. And then the last line, the green dash line, provides a view of what happens when you combine these two transformations, which is typically what we do for subsets of channels that we assume would have a decay effect, but we also want to model the saturation. Now, recently, some statisticians at Google actually proposed building MMM using Bayesian methods to model these saturation and lag effects. And there's 4 key benefits to this approach as we see it, and this is what really got us excited about this basic framework. So first, in a Bayesian method, you have the ability to set constraints on your model parameters using priors. And so for us, this is useful because we would assume, and we would not want any marketing activity variables, or marketing spend variables, to have non-negative effects, right? We assume that marketing should always at least have a positive or 0 effect. Second, the inclusion of priors allows us to incorporate our existing knowledge about the effects of advertising, and that can come from expertise of our stakeholders, but primarily we get that information from external benchmarks that we extract from A/B tests or lift tests or geo experiments. So we have an external ground truth, and we can use that basically to tune the parameters of our model to make sure that it's lining up with what we know about how each channel should be working. Thirdly, we can learn the parameters for our transformation functions, our saturation and our decay functions, as part of the model fitting process. And in particular, what's important is that we can also get estimates of uncertainty in those functions. So typically in an OLS framework, finding those parameters, the mu and the alpha, would require some kind of iterative optimization process that would likely involve some manual tuning. And then lastly, as we're probably all familiar with, Bayesian models produce a nice generative model that is well suited to doing simulations. Okay, so what does our media mix model look like? So I'm going to return to the basic formula here and lay out the structure of the likelihood and the priors as I walk you through it. So our likelihood is going to be defined based on the expected value of new customers we acquire each week. We're going to need to set a prior on the beta for our marketing channels. We'll also need to set a prior for the alpha parameter of our Adstock transformation that we apply to a subset of our channels. We need a prior for our mu parameter that controls the saturation curve that we fit for each channel. We're also going to need to set priors on the betas for our control variables, and then we'll need a prior for our noise term, which plugs into our likelihood. So this is the basic layout of the model. On the left side here, we have our likelihood, which, as mentioned, we define as a normal distribution. Mu is basically going to be a function of the linear model. And our sigma term will stand in for the standard deviation. Now, the model that I'm going to walk you through has 5 control variables and 12 channels in it. All of the marketing channels are transformed with a saturation function, but only a subset are transformed with Adstock to represent and try to capture decay effects. So we'll start here with the control variables. So we set priors there using a normal distribution and a sigma of 0.25. Now, I should note that all of our input variables, controls, marketing channels, and our dependent variable, our outcome, which is weekly customers acquired, are scaled so that they um, are between 0 and 1, right? So this is going to make it easier for our nuts sampler to explore the probability space. And this is why you see fairly low values on our sigmas here. So next we set our priors on our marketing channels. And as I noted, we want those all to be non-negative. So here we're going to use a half normal with a sigma of 5. For the subset of channels that we transform with our Adstock function, we use a beta distribution with an alpha of 3 and a beta of 3. So that gives us that nice rounded probability distribution function with a peak at 0.5. For saturation, we set a prior on our mu parameter as a gamma with an alpha of 3 and a beta of 1. And this ensures that our mu parameter is going to be positive. And lastly, we model, or we set the prior on our sigma term using an exponential distribution. And I should note that the priors we're using for our saturation and lag functions here are taken directly from Jin and colleagues. These are their recommended prior sets. So what does the model look like in code? This is the basic layout. We start basically by creating an empty list. And what we're going to do is iterate through groups of variables. And we're going to build up the priors and then add those to the list. And then at the end, we're going to sum those up to represent the mu parameter for our likelihood. So in this first section, we're going to iterate through our list of channels that can have both decay effects and saturation effects. So here we set our prior on the beta, which is the half normal. And then here you can see we use that nested transformation. So we're first transforming the marketing spend with our Adstock, and then that transformed version is fed to our logistic reach function, which is going to model our saturation. So for those channels where we only expect saturation and we don't want to have any decaying Adstock effect, we simply only apply our logistic reach function. So same basic setup here. We set the prior on our beta and then define the prior for the gamma and apply the transformation function. Next, we're defining the priors for a set of continuous control variables. So we have a set of variables that are basically monetary values. And so those can range from 0 up to infinity in theory, but they're real values that can take on floats, if you will. So we set a normal prior there with a standard deviation of 0.25. And then we have a set of categorical control variables. And here we're using an indexing method where we fit a prior, we define a prior for every level of the categorical variable. And this is generally a technique that makes it a little bit easier to find appropriate priors and fit them correctly. And then lastly, we define our likelihood. Again, this is a normal distribution. The mu is going to be defined by the sum of all of our response variables. And our standard deviation will be defined by our prior sigma, which is an exponential. So just to dig a little bit deeper into these transformation functions, because this is one of the main challenges that we encountered when trying to implement this model. So when it comes to the geometric Adstock, because of the nature of this transformation, we have to fall back on TensorFlow vector and matrix operations. So in the first step, we define a vector of weights, which is based on our decay rate alpha, and that is extended out over a length L. And typically we set that to be 12 weeks based on the recommendations from Jin and colleagues. And then we define a set of vectors, empty vectors of the same length, and then basically take the dot product of the two to get our weighted estimate of the outcome, or sorry, the marketing channel variable over the time frame that we want the decay to happen. For our logistic function, it's a little simpler. We just apply the function directly to our spend variable. And because we're only defining a discrete point one at a time, there's no backward or forward movement. It's a pretty straightforward transformation. Okay, so a little bit about our workflow. So typically when we're building the model and maintaining it, we start off with a baseline model with very weak informative priors. We fit that model, and then we compare those results, the parameter estimates we get, to our external benchmarks that are coming from A/B tests, lift tests, incrementality tests, and so forth. If we see a good calibration, we can leave it at that and move on. But typically, we need to do a little bit of tuning. So at that point, we work to adjust our priors, shifting them upward or downward, or narrowing them as we need to make them strict in order to help calibrate the specific marketing channel estimates so that we can line them up to our external benchmarks. And then we run through the model fitting again, do a comparison, and we do that as long as it takes to get the model calibrated to our external benchmarks. And then once that's done, we have some results that we can extract for our stakeholders and report out. So this is where we get into some of the applications that we found for this model in particular. There's a number of different use cases that we currently have for the model that include primarily strategic insights. So how well is our marketing working in total, and how is it working at the channel level? We also use the model in doing testing and simulation for some of our marketing activities. And we've also more recently begun using it as part of a forecasting pipeline that our stakeholders in finance and operations find helpful. But right now I'm going to focus specifically on our strategic insights piece, because typically this is really what a media mix model is for, which is you extract estimates of the incremental or true efficiency of your channels, and then from that you can have a method or insights into how you can change the mixture of spend across your channels, how you can distribute that spend to get the most efficient mix of marketing possible. So one of the first things we typically do is just we look at the saturation curves that we can extract from the model results. So at the top here, you see an example of a channel that we would say has low saturation. And this generally tells us that this is a channel that has room to grow. So you can see here at the point of our maximum spend, the reach curve is still pretty linear. So this tells us we could actually spend more than what we have historically, and we would still be within a range of acceptable efficiency. By comparison, on the bottom here, we have an example of a high saturation channel. So in this case, we can see that at levels of historical maximum spend, we're already getting into territory where our marketing is starting to lose effectiveness and efficiency. And from this, we can also get an idea of what the optimal range of spend is for this particular channel. So it would be somewhere in the portion of the curve that is linear. We can also take a look at our decay or Adstock curves to get a sense of, how long of a lag we see in particular channels. And this is beneficial because when a channel has a fairly long decay, that might suggest that we can spend a little less in any particular week and extract more value and efficiency out of that particular marketing channel over time, because that smaller input is going to have a longer lasting effect. So we're going to get a little more bang for our buck. So as you can see here, this red line represents a channel that has a fairly long decay of about 0.82. So, this is a channel where we might be able to pull spending back a little bit and squeeze a little more efficiency out of it. By comparison, the channel represented here in the blue line has a much shorter decay of about 2 weeks. So we still might be able to get some additional efficiency from this channel, but wouldn't be as much as if the decay was a lot longer. Now, really, the ultimate goal, as I prefaced before, is to use the parameters that we extract from models. So the channel betas, the shape of the saturation curve as we fit it through the mu parameter, and the length of any decay effects that we estimate through our Adstock function fitting. And we can plug those into a constrained optimization formula. And typically what we want to do is try to maximize the number of activations that we can get in a particular time frame based on the coefficients from the model, subject to constraints around the total budget that we have in a particular week, let's say, and the amount of that budget we're willing to put towards any specific channel. So for example, we might have a channel that currently represents 20% of our budget, but from the model's perspective, it's not very efficient. So we might want to shift the spending down, but we still might not want it to go completely to zero. So we might say, give us the optimal amount of spend within the range where we would only give 15 to 5% of our budget to that particular channel. And so from this constrained optimization, we can get recommendations about how to shift our spend around that takes into account saturation and lagged effects. So in this case here, in this example, we are basically seeing that channels 1, 2, 7, 8, and 10 are highly efficient, and there's opportunities to increase the spend there in order to maximize the overall efficiency of our spending. By comparison, channels 4 and 5 and 9 are not as efficient as we might want them to be, and so we might want to reduce spend there by a certain amount to make sure that we're not spending in a range that shows a diminishing return. So that concludes this presentation. I appreciate your time and attention and look forward to your questions in Discourse. Thank you very much.